Under ideal conditions, the currents in a telephone circuit, simplexed for telegraph, look like this. Since both sides of the line are alike, this circuit is balanced. The currents in a perfectly balanced phantom group look like this. But in the field, circuits are often unbalanced. Because of this, simplex and phantom circuits produce their own special trouble symptoms. Cross-ringing, crossfire, relay chatter, and the most common of all, crosstalk.
Major Kurtzer, about that ration report. About that ration report.
X-ray table.
Who the hell's in on this line?
George, Oboe, Tear.
These symptoms usually occur in combination. Understanding them will help you to diagnose trouble and tell you which circuits, if any, are still usable. To understand the symptoms, we must first study the causes behind them. Let's take the simple example of a telephone circuit which has been simplexed for telegraph. Suppose the line is accidentally shorted. What happens to the telephone current? Because of the short, it never reaches its destination. The telegraph current, however, follows its normal path. It divides equally and flows along the two line wires. At the short, the two halves of the current oppose each other, and so no current flows through the short. We can see then that the telegraph channel is unaffected by the short, but the telephone channel is useless until the short is cleared. Here is our circuit restored to normal. The resistances of the two line wires are equal. The circuit is balanced. But sometimes the resistance of one wire is greater than that of the other. A bad splice in one wire can cause this. Now the circuit is unbalanced. Because of the unequal resistances, ringing current flows through the telegraph sets. But unless the unbalance is great, the amount of diverted ringing current will be too small to actuate the telegraph relays. As usual, telegraph current flows to the midpoint of the winding of the repeating coil. Because of the unequal resistances, however, the current no longer divides equally between the two halves of the winding, and the magnetizing effects of the two currents no longer cancel each other. Thus, current is induced in the other windings of both repeating coils at the beginning and end of each impulse. This produces crossfire interference in the telephone channel. These are called key thumps. Other than being an annoyance, they do not affect telephone communication. And both ringing and voice current get through without interfering with the telegraph. The extreme condition of this unbalance occurs when one line wire is open. Now, all the telegraph current travels over one wire, and the current induced in the telephone circuit is at a maximum. Telephone signaling is usually still possible, even with the open line wire. The low-frequency ringing current uses the available half-winding of each repeating coil, the telegraph sets, and the earth for its path. The ringing signal gets through, and this time it is strong enough to make the telegraph relays chatter and will cause audible interference in both telegraph sets. The higher frequency voice currents, however, are choked down by the telegraph sets to too small a value for an audible signal. Since conversation is impossible, the telephone channel is useless until the break is repaired. Another condition which causes interference is an accidental ground on one of the line wires. Part of the telegraph current is diverted by the accidental ground. However, enough generally gets through to operate the other telegraph set. Currents are unbalanced in both repeating coils, and current is induced in both the other windings. Notice that the induced current is greater at the sending end than at the receiving end. When we ring on the telephone channel, some ringing current flows through the near telegraph set because the lower half of the repeating coil has a shortened path through the accidental ground. This causes an unbalance in the normal ringing path, so that a small amount flows through the far telegraph set too. Because of this, the ringing current delivered to the far switchboard is less than normal. Voice current, however, is unaffected. We have seen before that this higher frequency current cannot travel through a telegraph instrument. Consequently, it follows its normal path. Ordinarily, the telegraph channel is still usable unless the diverted ringing current is strong enough to cause interference. The telephone channel is still okay too, but its quality may be somewhat impaired by key thumps. And like any other grounded circuit, it's apt to be noisy. So much for the Simplex. Here is what we have seen so far. When the line is shorted, the telephone channel's no good. But the telegraph channel's as good as ever. When the resistances of the two line wires become unbalanced, telephone current flows through the telegraph sets, but it's rarely strong enough to interfere with telegraph communication. The telegraph does interfere with the telephone, but not sufficiently to disrupt telephone communication. When one wire is open, telegraph is still okay. Ringing current gets through too, but interferes with the telegraph channel. Voice current is blocked. When one wire is grounded, both channels are generally still usable. Telegraph current is weakened, though, and interferes with the telephone. Ringing current is also weakened and may interfere with the telegraph. Voice current is unaffected. Now for some typical examples showing the effect of line trouble on a phantom group. This phantom group consists of 3 telephone circuits. Here, telephone ringing and voice currents act alike, so we will confine our demonstration to ringing current only. If one of the side circuits is accidentally shorted, its reaction is the same as a shorted simplex. The ringing current of the faulty circuit never reaches its destination. When we ring on the phantom, however, we can see that it is unaffected because the two halves of the phantom current are traveling in the same direction. When they reach the short, they buck each other, and no current flows through the short. That is exactly what happened in the telegraph channel of the shorted simplex. The other side circuit is unaffected. The faulty circuit is no good until the short is cleared. It follows that if both side circuits are shorted, both are useless. But the phantom is still okay. Now let's assume that our trouble is an open in one of the side circuits. This is the extreme condition of unbalance. We will ring on the phantom first. The phantom current travels through the unbroken side circuit in the usual way. But in the open side circuit, all the current goes through one wire. This induces current in both the other windings of both repeating coils. In the faulty circuit, it produces interference. Ringing on the faulty side circuit produces a weak current, which finds a return path through the phantom. This causes interference in the phantom. The unbroken side circuit operates as usual. The phantom interferes with the open side circuit and the open side circuit interferes with the phantom. If we discontinue the use of one, the other will not be subject to interference. Which one should we stop using? Well, transmission in the open side circuit is weak, so we eliminate it, and the phantom will work okay. What happens if both side circuits are open? This one's tricky, for now, both sets of repeating coils are unbalanced. Ringing on either side circuit, we find that current flows through every possible drop in the phantom group. The jack we ring on is, in effect, connected in series to the other 5 drops. Either side circuit then interferes with both the phantom and the other side circuit. Ringing on the phantom, we find that the current is stronger, but the path is the same. Consequently, the phantom interferes with both side circuits. We've got 3 circuits interfering with each other. No matter what we ring, we hit the jackpot. We can still use one circuit by eliminating the other 2. The phantom is strongest, so we stop using the side circuits. They can't interfere with the phantom if we don't use them. Until the 2 open side circuits have been cleared, we can at least use the phantom. Here's a very common trouble which also affects all 3 channels: a cross between the 2 side circuits. Most of the current originating in the west phantom is confined to the path which has been made by the cross. This heavy current causes strong interference at the west end of both side circuits. Notice, however, that some current gets to the east end of the circuits, giving a weak signal on the phantom and weak interference in both side circuits. Ringing on one of the side circuits, we can see that the current follows a similar path and causes interference in the other two west drops. And here again, the circuits are affected at the east end. We've got three circuits interfering with each other again. But this time, two can be made to work fairly well. If we cut out the phantom connections at both ends, the two side circuits can be used. Actually, we no longer have a phantom group. What we do have is two metallic circuits accidentally crossed, and we won't get any more interference between them than is usually caused by this condition. A short on a side circuit affects only that circuit. An open in one wire of a side circuit causes mutual interference between the side circuit and the phantom. When both side circuits are open, all three circuits interfere with each other. When the two side circuits are crossed, all three circuits interfere with each other, especially at the transmitting end. This isn't the whole story. Each of the examples you've just seen has shown only one kind of trouble at a time. Friendly vehicles and troops, unfriendly elements, and enemy action bring on combinations of shorts, grounds, opens, and crosses. An understanding of the basic theory, however, will help you handle these combinations yourself.